Now we discussed the photoelectric effect in detail. So when we explain the photoelectric effect, one thing is clear: this photoelectric effect cannot be explained using the wave theory of light. If we want to explain the photoelectric effect, we have to consider light as a particle. So that particle is called photon. So photon means it is the light particle, or it's a quanta or a packet of energy. So light can be considered as a packet of energy or a particle, and that particle is called as photon. Now if you go to the very basic idea about the photon, the first point is the same thing. When light is considered as a particle, that particle is called as photon. And each photon carries some energy. So energy of the photon depends on its frequency also. So when we consider light as a wave, there is a frequency. So that frequency is related here. So the energy carried by each photon is given by E is equal to h nu, where nu is the frequency of the light and h is our Planck's constant. So here if you take any radiation, for that radiation we can consider this as a particle, and the energy of the particle is given by E is equal to h nu, where h is Planck's constant and nu is the frequency. Similarly, for this one we have a momentum also. There is something confusing in that one, because we are considering light as a particle means we are considering it as a massless particle. So when mass is not there, from where this momentum comes? Because previously we studied mass, this momentum is equal to m into v. But here what happens is, it is a massless particle means photon's mass is 0 when it is at rest. So its rest mass is 0, but photon is not at rest. Photon is always moving with the speed of c. So it is having an effective mass. So using that effective mass, we can get the momentum of photon. So momentum of the photon is given by P is equal to h nu by c. So like that we can calculate the momentum also. That is very important. Even if we consider light as a massless particle, there is a momentum for that one because of the moment. There is an effective mass for that one. When it is rest, there is no mass for that one. Now all the photons or all the light with a frequency nu will have the same energy. So the energy depends on the frequency. Okay. Now after that, if you take these photons are already we discussed, it is massless, and like that it is chargeless also. It is a neutral thing. So if you have electric field or magnetic field and all, this photon will not bend. Photon will go straight. It's just like a electron or the charged particle. It will not bend in electric field or magnetic field. So it is not affected by electric field and magnetic field. And this particle can undergo collision. Two photons can undergo collision. When two photons are undergoing collision, the other rules, just like the momentum conservation, all those things are true there. But the number of photons may change. After collision of two photons, sometimes the number can change. The total number of number of photons before collision and after collision can change. But the momentum remains same. So in some collisions, one photon can be converted into normal energy itself, or a new photon can be created. All these things are possible in the case of photon. Now, when we consider the wave behavior of particle, each particle will behave like a wave also. So for such a wave, there should be a wavelength. So this wavelength is given by the de Broglie relation. The wavelength lambda is given by h by p. So where this lambda is the de Broglie wavelength or wavelength of the particle, and h is Planck's constant, and p is the momentum, or p is mv. So the wavelength lambda is given by h by p or h by mv, and this lambda wavelength is called as de Broglie wavelength. And if you take the actual wavelength, you can see it depends on the momentum. So for small, very small particles like electron or still smaller particle, so there we can see, we can feel, or we can experience the wave nature in some experiments. But if you take a big object like a cricket ball, there the momentum is so high so that the wavelength is negligibly small. We cannot feel the wave nature of that one. But still each and every object will behave like a wave. But the wavelength will be negligibly small, so that we will not consider that one. But in the case of electron and all, it behaves like a wave. That wave property of electron we are using in the case of electron microscope. Because when the wavelength is very less, the resolving power will be high. We studied in the previous chapter. We already discussed in the previous topic that the electron can behave like a wave. So when the electron is behaving like a wave, what should be the wavelength of that one? So we can calculate that one like this. See here, the kinetic energy of electron is given by K is equal to E into V, which we already discussed. And from our mechanics, we have the kinetic energy K is given by half mv square. This K is equal to half mv square. We can write it as P square by 2m also. Now you see here, if you combine these two, we can write P is equal to root of 2mk. This K you can replace here, so you will get it as root of 2mev. So this is the equation for the momentum. Now from our de Broglie wavelength, we have lambda is equal to h by p. So this p we can replace here, so you will get lambda is equal to h by root of 2mk. This k you are replacing here, you are getting ev. Now you see this one here, the wavelength is given by lambda is equal to h by root of 2me into v. Here this h is Planck's constant, and we can substitute the value of Planck's constant. This 2 also is a constant, m is mass of electron, that is also a constant, and E is the charge of electron. All these values are constant other than V. So if you put all these values, we can get the wavelength of electron accelerated by a potential of V will become lambda is equal to 1.227 divided by root V nanometer. It's very important when you are doing calculation and all, you should remember it is 1.227 by root V nanometer.